All right, here are the solutions to page 237, 1 through 9 odd, and then the AP page 5, number 14. All right, so in question 1, dealing with area, it says the radius r and area A of a circle are related by the equation area is equal to pi r squared. Write an equation that relates dA over dt to dr over dt. So all we have to do is take the derivative of both sides. So on the left, we're going to have dA over dt, and that's going to be the derivative of pi r squared with respect to t here. So we still have dA over dt. Now this will just become 2 pi r, and again, just like implicit differentiation, we have to multiply by r prime, or in this case, we'll write it as dr over dt. And that relates dA over dt, the rate of change of the area with respect to time, to the rate of change of the radius with respect to time. Number 3 deals with volume. It says the radius r, height h, and volume v of a right circular cylinder are related by this equation, v is equal to pi r squared times h. Couple parts here, a few parts rather. How is dv over dt, the rate of change of volume with respect to time, related to the rate of change of the height, dh over dt, if r is constant? So when we go to take the derivative, we'll have dv over dt is going to equal d of pi r squared times h over dt, but we're treating r as a constant, so then we get dv over dt is equal, this will just give us, if h is the only variable, we'll be left with pi r squared, but then times the derivative of h, kind of like implicit differentiation here, we would normally have to write like h prime, but instead of writing h prime, we're writing dh over dt, and that relates the two rates of change together. For part B, just the opposite. We want to relate dv over dt to dr over dt. This time h is constant, so we'll still have dv over dt is going to be the derivative of pi r squared times our height over dt. But this time h is a constant, so we'll bring the exponent down. So we'll get a 2 pi r times h, or 2 pi h times r, and then times r prime, or dr over dt. And that's our answer. Now for part C, they want us to relate all three together, dv over dt to dr over dt to dh over dt. This time neither r nor h is constant, so we'll start off the same way. But this time we have to use the product rule over here because both r and h are variables. So treating pi r squared as u, so we'll have u. V prime just becomes dh over dt plus v, which is h, times the derivative of pi r squared, so we'll get a 2 pi r times dr over dt. And you can rewrite this as 2 pi rh or 2 pi hr, but that would be our answer for part C. Okay, number 5 deals with diagonals. It says if x, y, and z are lengths of the edges of a rectangular box, the common length of the box's diagonals is s is equal to the square root of x squared plus y squared plus z squared. We want to relate all of these rates of change together. So again, we're going to start with taking the derivative of s with respect to time. I'm going to rewrite this as the quantity to the 1/2 power. So now I will have ds over dt is going to equal the chain rule first, 1/2 times this quantity to the negative 1/2. Then when I go to multiply by the derivative of the inside stuff, that's where dx over dt, dy over dt, dz over dt are going to show up. So we're going to have 2x times dx over dt plus 2y times dy over dt plus 2z times dz over dt. Now technically we could leave it like this, but there's usually, and there is going to be more stuff we have to do with it, so it is in our best interest to try to simplify this as much as possible. So right here, really, this 1/2, I could take and distribute to each term over here, so all the 2's are going to go away. The 1/2 and all the 2's are going to go away. So what that's going to leave me with is a fraction, x times dx over dt plus y times dy over dt plus z times dz over dt And then I could just move this to the denominator and just make it the square root of x squared plus y squared plus z squared. Okay, now for number 7, in a way this is kind of like the 6-step plan, but not written out identically in an identical way there. So for part A, it's giving us this formula that's right here. And they want us to ask, or they want us to figure out what is the value of dV over dt. So if we go back up to the little paragraph here, it says that V is increasing at a rate of 1 volt per second. So that's the rate of change in the volts here. If it's increasing, it's positive, 1 volt per second. For B, what is the value of dI over dt? So it says while I is decreasing at the rate of 1/3 amps per second. So that means dI over dt, since it's decreasing, that's negative 1/3 amps per second. Question C is write an equation that relates dr over dt to dv over dt and di over dt. So we want to start with dr over dt. So we're going to solve this for r. We're going to solve this equation for r. So that becomes v over I. And then we could take dr over dt is going to be the derivative of this quotient. So we could use the quotient rule, or we could say that this is v times I to the negative first. So that we have dr over dt. So I'm going to use this right here. So we'll have uv prime. So we're going to have v times a negative I to the negative second times di over dt. And then plus I to the negative first times dv over dt. Because that's leaving this the same and then taking the derivative of v. And this we want to clean up because there's a little bit more we're asked to do in part D. So this just becomes, we could say, negative v over I squared times di over dt, and then plus 1 over I times dv over dt. Because now in part D, it says find the rate at which r is changing, so that's dr over dt, when v is 12 and I is 2. And they want us to answer, is r increasing or decreasing? Explain. So we would say that dr over dt is equal to negative v over I squared, so that's negative 12 over 4. di over dt from part B, that was negative 1/3. And then 1 over I, so that's 1/2. dv over dt, that was 1. So this gives us 12 over 12, so that's 1 plus 1/2, so we get 1.5, or 3/2. And R was given in ohms, so this is ohms per second. So since this is a positive result, we would say R is increasing. And again, think about this. This is our first derivative, dr over dt. So if that's positive, that is telling us that our function is increasing. So R is increasing. All right, and then let's take a look at number 9. For this, we definitely want to use the 6-step plan. Changing dimensions in a rectangle. The length L of a rectangle is decreasing at the rate of 2 centimeters per second, while the width W is increasing at the rate of 2 centimeters per second. When L is equal to 12 centimeters and W is equal to 5 centimeters, find the rates of change of A, the area, B, the perimeter, and C, the length of a diagonal of the rectangle. And part D, which of these quantities are decreasing, which are increasing? Explain. So first, let's start with a picture. And we're just going to draw a rectangle. Now what's happening here, the length is decreasing and the width is increasing. So if this base here is my length, that's going to be decreasing, and then my width is increasing. So eventually I'm going to have a rectangle that perhaps looks like this. So this would be our L, this would be our width. And it does mention a diagonal, so I'm going to put this in here as well. There's our diagonal. Call that D. So the step 2 is, what do we know? So let's go back and read this. The length is decreasing at a rate of 2 centimeters per second. So I'm going to say that this is dl over dt. Since it's decreasing, that's negative 2 centimeters per second. And the width is increasing, so we would say dw over dt. That's going to equal a positive 2 centimeters per second. Step 3, what are we asked to find? Well, a couple things. In part A, we're asked to find dA over dt. In part B, we're asked to find dP over dt. And then part C, we're asked to find, this is why I used a capital D, the rate of change of the diagonal with respect to time. All when L is equal to 12 centimeters and W is equal to 5 centimeters. Step 4 is we need an equation. We'll kind of map this out in all 3 parts. So for part A, we're going to relate this, we're going to use the area of a rectangle, so A is equal to L times W. B, we need the formula for perimeter, so P is equal to 2L plus 2W. And then C, we need something that involves a diagonal, which would be the Pythagorean theorem, so we would say D squared is equal to L squared plus W squared. Now step 5, we're going to differentiate with respect to time. So for A, we're going to have dA over dt is going to equal the derivative of our length times width over dt. So that dA over dt is going to equal, again, uv prime, so it's going to be L times dW over dt plus W times dL over dt. For B, we're going to take the derivative of the perimeter. So that dP over dt is going to equal 2 times dL over dt plus 2 times dW over dt. And then for part C, we're going to take the derivative of d squared over dt, and then the derivative of the other side, L squared plus W squared over dt. So this will become 2d times the derivative, so d of capital D over dt. This will become 2L times dL over dt plus 2W times dW over dt. We could simplify this. Notice they all have a 2 here, and I want to get the d over dt by itself. So we could just say that the derivative of the diagonal, everything divides by the 2 there. So then we could just have all of this divided by d. So we'll just have L times dL over dt plus W times dW over dt all over d. So this will help us with step 6 when we go to evaluate. So again, L is 12 centimeters and W is 5 centimeters. So for part A, we would say dA over dt is going to equal 12. Now dW over dt, that was 2, and W is 5, and dL over dt is negative 2. So 24 minus 10 will give us 14, and this is area, so square centimeters per second. That is the rate of change of our area. We would say the area is increasing because dA over dt is positive. For b, we would have dp over dt is going to equal 2 times dl over dt, so that's 2 times negative 2 plus 2 times a positive 2. So that would actually be 0. Perimeter is linear, so centimeters per second. And doesn't that make sense? Because no matter how we rearrange the rectangle, if it's the length is decreasing and the width is increasing, the perimeter is going to stay the same no matter what. All right, and then for part C, we're going to have 12 times negative 2 plus 5 times 2. Now off to the side, we need to know what d is. So if d squared is equal to L squared plus W squared, that would give us 144 plus 25. So D is going to equal 13. So we'll get negative 14/13 centimeters per second. And that would tell us that our diagonal is, the length of the diagonal is decreasing. Because its rate of change is negative. Now, if we use negative, that's fine, but if we say the length of the diagonal is decreasing, if we use the word decreasing, we no longer need the negative. So we would say the length of the diagonal is decreasing at 14/13 centimeters per second, or we would just say the rate of change of the diagonal is negative 14/13 centimeters per second. All right, so let's take a look at the AP problem. So we're given this function here, f of x, and we're asked to find the x value in which f has a local max. So first we want to find the derivative. So this is e to some power, so that stays the same first. Then we multiply it by the derivative of the exponent, so we'll get a 3x squared minus 4x minus 4. And then we'll set this equal to 0. It's never going to be undefined, so we would say f prime of x is only going to equal 0 when this trinomial equals 0, because e to any power is never going to equal 0. And we're not allowed to use a calculator. We can factor this. Say 3x and x, and it looks like 2's are going to work here. We'll have a negative 6x plus 2x. So when x is equal to negative 2/3, or when x is equal to 2, so we'll make our first derivative number line. And I'm going to substitute these back into the factored form here. So let's say we tested a negative 1. Over here, this would be negative and negative, so we're going to get positive here. Let's say we test 0, we'll get a negative, and say we test a 3, we'll get a positive. So we would say f is increasing, decreasing, and then increasing. So we would have a local max at x equals, oh, sorry, is a min. We would have a local min here at x equals 2. So that was answer E. All right, so after looking at this video, please let me know if you have any questions.